Okay.
So let's continue with our second talk. So we have Sarah Strikwerda from University of Pennsylvania from the United States, and Diego Souza will introduce her. So please, Diego.
So thank you very much, Anna. Professor Sarah, she defended her PhD last year on May in the North Carolina State University under the supervision of Professor Lorena Bosio, and now she's current at the University of Pennsylvania as a postdoc researcher, right? And today she's going to talk about optimal control and multiscale coupling of an elliptic and parabolic PDE. Okay, so thank you very much for accepting deliver talk here for us. So you have the word.
Thank you so much for the invitation to come here and for the organization and the introduction. I'm happy to be here. So today, as Diego said, I will be talking about optimal control and multi-scale coupling of an elliptic parabolic PDE. And to start out with, I'm going to talk about an application of this work. What really makes me interested in these problems is the application that they have to glaucoma. Glaucoma is the leading cause of blindness worldwide, and it's characterized by damage to the optic nerve head. And one way that it can form is if you have a drainage canal that is blocked or like fluids can't flow through, there might be some pressure buildup, and pressure in the eye globe results in damage to the optic nerve head, and that is not good and what leads to the blindness. And so we want to try to understand the dynamics of this better so that we can learn how to treat it better as well. Right now, the treatments are related to reducing intraocular pressure. This makes sense because the risk factors are elevated intraocular pressure, age, race, and medical history. However, many people have elevated IOP and they don't get glaucoma, and some people have normal IOP and they still develop glaucoma. So it seems that there's more going on with the dynamics, so we want to be able to understand that better. Right now, with the treatment reducing intraocular pressure, the treatments are done using medications, laser surgery, or traditional surgery. And the primary location of damage leading to glaucoma is actually in this lamina cribrosa. So this is the base of the optic nerve head, which in that other picture, that's where we said damage can occur if there's pressure buildup here. And if we zoom in on that, we have these different regions, and we're talking about this laminar region. And you can kind of see how there's like fluid flowing through this tissue. And so we think about it as a poroviscoelastic tissue. And so what we do then to model it is use poroelastic models. So poroelastic models have been used for a while. Terzaghi developed a one-dimensional one in 1925 to describe soil consolidation, and then Bio generalized that to 3 dimensions in the 1940s. And these models have been really useful in looking at applications in geoscience and like with applications in petroleum engineering. But then more recently, these models have been used in biological applications because just as dirt can be viewed as this solid with these pores that the fluid is flowing through, we can also view our tissues like that. Primarily, we want to think about that if you have a tissue with like lots of very small capillaries flowing through it, we don't really want to model the fluid flow in each of those capillaries separately. So instead, we think about the whole thing as just this porous medium and think about the fluid flowing through in that way. And so here is the model. So first we want to have a balance of linear momentum. So the divergence of the stress tensor should be equal to a force. And this stress tensor here is given by 2 times the symmetric gradient of U. So this is the Jacobian of U plus the transpose of the Jacobian of U. And then we also have the divergence of U with the identity tensor, and we subtract P with the identity tensor. And so then here, this U is the mechanical displacement. So a lot of times people in equations like this are using U for fluid velocity. That's not the case here. U is our mechanical displacement. It's how the solid is moving. And then P is our fluid pressure. And so now we have fluid content is this zeta that we put the time derivative on. And this second equation is coming from the balance of mass. And here we have zeta is equal to C naught P plus alpha times the divergence of U. But C naught is the constraint-specific storage coefficient, and alpha is the Biot-Willis coefficient. And in biological applications, C naught is actually 0, and alpha is equal to 1. Now, this is because of the assumptions of incompressibility for the fluid and solid components. And so the divergence of U is also the solid dilation, and so it makes sense that the fluid content and the solid dilation have to be connected if we have an assumption of incompressibility for the whole mixture together. And also, I should say that that also comes from the assumption that we're assuming that the pores are fully saturated with the fluid, so there's no like air pockets in there as well. It's either solid or fluid. And then the second term here is now V, which is the fluid velocity. And so to think more about how that's related to P, we have phi is given as the porosity. And as I said, phi could also be thought of as the divergence of U. And then here we write it as the fluid content plus some baseline porosity. And that fluid content for us is just the divergence of U. And so then V is equal to negative K, where K is a permeability tensor acting as a function of porosity times the gradient of P. And here K is actually going to be a little function K, that's the function of phi, and times the identity tensor. It could be nonlinear. For example, this is the formula called the Kármán-Kezeny formula. And this formula should be dependent on the sphere size and shape. And so there's a couple different formulas that people will use, but really, if we're just talking about the analysis, we just make the assumption that whatever the function is, it should be bounded below, away from 0, and also bounded above. And then also we can say that K could just be a given function of x and t. So this would reduce the problem to a linear PDE because we'd get rid of that nonlinear coupling. Usually with the analysis, we want to start with the linear coupling, so we'll study it that way. And even more simpler, the system is often studied with K just taken as a constant. So then you just have the divergence of K, or the divergence of negative K grad P. So it kind of becomes this Laplace term. And then we want to add boundary terms to our system. So for the application that we have in mind, so the lamina cribrosa, the boundary terms that we add are going to be split onto 3 different parts of the boundary. So first, we're going to split the boundary into 2 parts. We're going to split it into gamma n and gamma d, where on gamma n, we have these Neumann boundary conditions given by having a boundary condition on the stress and on the fluid velocity. And then on gamma d, we're going to further split that into gamma dp and gamma dv. On all of gamma d, we have a Dirichlet boundary condition on u, that u should be equal to 0. On gamma dp, we say that p is equal to 0, and on gamma dv, we have v dot n is equal to psi. And then we have an initial condition given here, where the divergence of u should equal d naught. So we are studying, we want to think about studying these equations from an analysis perspective. And so to do that, we're going to be considering weak solutions. And so we define these function spaces that help make sure that those zero boundary conditions are satisfied. So this is a function space that we want P to belong to in space. And so here it should be H1, but have zero trace on the boundary gamma dp. And for U, we want it to belong to this vector valued function space where it is H1 in space and has trace 0 on the boundary gamma d. And as long as the measure of gamma d is greater than 0, then this is a valid inner product for this space. So that's what we use. And you'll notice that it pairs really well with what we had as the stress tensor before. So our stress tensor from before in the weak form just becomes this bilinear form here, minus P paired with the divergence of the test function here. And then in our second equation, we notice that we put the time derivative over on the test function here. And so we really only need to require that U and P belong to L2 in time. And then a lot of people have studied this form of weak solution, so we'll review some of that. In 1977, Oreo and Sanchez Palencia looked at this problem. They were looking at the linear problem where that permeability K is just a constant. And they had Dirichlet boundary conditions. Then they wanted to study the well-posedness, and they showed existence and uniqueness of a solution. Zenisek similarly did this, but he had mixed boundary conditions, and he used Roth's method and showed existence and uniqueness to this linear problem. And Showalter then came in and he wanted to use some monotone operator theory, and he was also able to show existence and uniqueness, and also with some of his operator theory, you can get existence and uniqueness of a solution to the problem where K is a function of X and T, as long as you assume that the time derivative of K is L2. And here Showalter and Sue worked on this problem further, and they looked at the nonlinear problem, but their nonlinearity was different. Rather than taking K as a function of the divergence of U, like I described before, they had K as a function of pressure because that has applications in geoscience. And so they were able to use some monotonicity properties of the nonlinearity to get their well-posedness. Osarek wanted to think more about getting more regularity on the solutions. And so he put Dirichlet boundary conditions on, and it had K just as a constant, and then upped the regularity of the sources and used Galerkin method and was able to get higher regularity on his solutions U and P. Cauchan and Meyer looked at the nonlinear case, and they were looking at the nonlinear case that I was showing before, where we have K as a function of the divergence of U. Now, something I forgot to mention is that let's see, all of these are in the what we call the incompressible case, where that C naught is equal to 0. So the fluid content is really just the divergence of U. Here, Cauchan and Meyer looked at the case where C naught is greater than 0. So their fluid content was given as C naught P plus the divergence of U. And also Oreo and Sanchez Palencia was also the case where C naught is greater than 0. And the reason why these cases where C naught is greater than 0 is studied usually before the case where C naught is equal to 0 is because the fluid content is what you put the time derivative on. And so to have C naught greater than 0, that means you get a time derivative on P And that added regularity ends up helping quite a bit. And so that is analytically normally the easier case. But then in 2016, Bochu, Guidoboni, Sacco, and Webster looked at the system similarly to Couch, Chen, and Meyer, where they used like a Roth's type method, but also accounted for the nonlinearity. But Bochu, Guidoboni, Sacco, and Webster were looking at the incompressible case where C naught is 0, so we just have that fluid content. In 2021, Bochu and Webster looked at this again. They really had wanted to use some kind of operator theory because the discretizing in time and space that is used in this 2013 and 2016 paper is just a bit tedious. And so they wanted a nicer way to do it. And so they wanted to use some kind of operator theory. The problem is that in the nonlinear case, to use some kind of like fixed point map to deal with this nonlinearity is actually quite challenging because at this point, the only result for uniqueness where K is a function of X and T required that K have regularity on its time derivative. And so then if we're taking K to be a function of the divergence of U, any fixed point strategy seemed to require extra regularity on the divergence of U in order to get uniqueness of a solution, which you would need for your map when you're looking for a fixed point. But then what they did in 2021 is instead they used a multi-valued fixed point map. So without the uniqueness, they just considered this multi-valued map. And that's how they overcame that. But then in 2022, they were able to actually get a result where they did have uniqueness of a solution where K is just a function of X and T, and you don't require high regularity on K. So then they're able to do a fixed point method for the nonlinear case without using this multi-valued fixed map. And I just want to point out that for these nonlinear cases, the results that these papers have are just existence results. And sometimes they talk a little bit about uniqueness, but the uniqueness results look like this, where you say that like if let's see, so there's at most one solution when PT belongs to this extra space, or some papers have other conditions, but the point is you can't just say that there is a unique solution, but you can say that there's only one solution in a certain class of solutions. And this is important because next I want to start thinking back to our glaucoma problem. We want to start thinking about an optimal control problem where we're trying to control the variables in here. And so the variables in the PDE are that mechanical displacement and fluid pressure. And these are important to study because changes in mechanical displacement lead to stress on the retinal ganglion cell axons, which communicate what you're seeing to your brain. So we don't want stress on those, and also can lead to changes in pore dimension. And both of these things can lead to glaucoma. Also, fluid pressure leads to tissue perfusion, which can also lead to glaucoma. So we really want to try to control this mechanical displacement and this fluid pressure. And so what we do is we use the sources in the PDE system, and we want to use these to minimize the difference between a mechanical displacement and a desired mechanical displacement, and a pressure and a desired pressure. We want to minimize these differences using one of the controls. So this is how we originally write the optimal control problem. But now really to think about if we have existence and uniqueness of an optimal control, what we want to do is change this U and this P to instead be the output of a control to state operator. So we introduce G, which is this map that maps a control, which we're using one of these as the control. We can use any of them. So it would map, say, F to the solution to the PDE with that given f. And in order for that map to be well defined, you really do need uniqueness of a solution. And so we, for our optimal control problem, reduce back to the case where k is a function of x and t, so that we can have a well-defined control to state map and reformulate this cost functional as just a function of q. And then once we have it just as a functional of q, because of how we wrote this cost functional, we have some squares here, we get a nice convex cost functional, and we can say that there does exist a unique optimal control. And I also just want to point out back to the application that this cost functional that we're seeking to minimize, this UD and PD would just be given from a mathematical setting, but from the application side, UD is available from experimental and clinical studies. So what we really desire to be that solid displacement, we do have that data. PD, we can't really measure the ideal pressure in the lamina cribrosa, and so that would just have to be estimated based on the solution computed for intraocular pressure at healthy baseline values. Okay, so as I said, we have existence and uniqueness of a solution to this optimal control problem. So the next thing that we want to do is say that we can characterize this optimal control in some way. And so what we can do is use a Lagrange multiplier method and to get this adjoint PDE system to help us characterize this optimal control. And this is helpful because one way to characterize the optimal control is through the time or through the derivative with respect to q of the cost functional. But this will actually result in having the adjoint of the control to state operator. Oh, I see there's a question. Susanna, go ahead. Okay, I'm not sure. Oh, are you there?
No, continue.
Okay. Okay. Susanna, if you want to ask your question later, feel free to interrupt. Okay, so we want to take the derivative of this, but the derivative will end up having the adjoint operator of the control to state operator. And so then using this adjoint system, we can get away from that because we barely have an understanding of how this control to state operator works. And so to talk about the adjoint of the control to state operator is hard to wrap our minds around, but instead we can have this adjoint PDE system where we can kind of see how things relate. And so the adjoint PDE system says, like, if you put this into the adjoint, then what you get out will either be M or H, depending on which control you're using. And this adjoint PDE system looks very similar to the original PDE system. One thing that is different, though, is that instead of having the divergence of the vector valued function having a time derivative on it in the second equation, instead we have the scalar valued function having a time derivative on its gradient in the first equation. And this is because of the coupled nature of the problem. And so this added some interesting aspects to the analysis, because a lot of times when doing optimal control problems, when you look at the adjoint PDE system, it looks almost identical to the original PDE system, except for it's reversed in time. But because we had that time derivative move, this is significantly different. So the well-posedness of the adjoint PDE system also had to be shown. And so we can show that if K is constant, then we have existence and uniqueness of a solution to this adjoint PDE system. And then what we want to do is talk about how do we now use this adjoint PDE system solution to characterize the optimal control. And so what we can do is we have a S bar is the optimal control. I wrote this in terms of the control S, but you can also write it in terms of F G, or psi, the other controls. So S bar is the optimal control to the problem with delta greater than 0 or PD minus P tilde belonging to this space, or with delta greater than 0 or PS belonging to this space. Then we can say that there exists this solution to the adjoint system which satisfies this. So this kind of tells us, like, if S bar is the optimal control, that and these things are satisfied, then this will also be satisfied. And then conversely, if S bar satisfies these things, and also there exists this solution M and H to the adjoint system which satisfies this, then we know that that S bar is the optimal control. And so this kind of helps us characterize the optimal control. And then the next thing that we wonder about is, okay, well, could we numerically approximate optimal controls? So I worked on this in the one-dimensional case. And so here I took the cost functional to be in terms of F, and I have U tilde and P tilde as a solution to the PDE system with these parameters set as is. And we see that as my algorithm ran, which I use the conjugate gradient method, the cost functional does reduce and settle in. So that's a good sign. And then these sources that I picked in the desired U and desired P, I picked those specifically where I knew of an F that would give us exactly that desired U and desired P, but I wanted to see what the algorithm did. And I suspected that it might not give it exactly because we have this additional cost for the control itself that might change things. And sure enough, if we look, this is the U that my system gave out, and this is the desired U. So we see those differences where we don't have the 5 maximums, we just have this one big one. And then with our P though, it looked like identical, so that was great. And then we'll notice that this is the F that it told me was the optimal F, and this is the F that I knew would actually give me the desired U and P. And so we can see here that certainly this F would have a larger L2 norm than this F right here. And so this kind of shows that if you really do want to have that cost for the control, then you might have to sacrifice a little bit of what that F is, but it still works for P and it's not too bad for you. The other thing though that I thought about after working on this is, well, what if there are like short spikes in pressure or changes in displacement? In terms of the glaucoma application, if you have short pressure spikes in your lamina cribrosa, that's going to be really bad because we're talking about the eyeball. But in the L2 norm, that might not be so bad. So the optimal solution might have these like peaks that aren't actually good. So that's something to think about. And so people study then state-constrained optimal control problems. So we've thought about that with our system as well, and we are in the process of working on that. But one thing with that is to put state constraints on your optimal control problem, you really need high regularity on your solutions. So right now we've reduced to the one-dimensional case, but we also need to be thinking about how we could get higher regularity on our solutions. And then the other question that I had was, back a few slides ago, near the beginning, we noticed that one of the risk factors of glaucoma is actually that if you have low blood pressure, but you have high intraocular pressure, that's when you're most at risk for glaucoma. And so this blood pressure, this like global blood pressure, has an impact on how at risk you are for glaucoma. But if we think about the PDE model that we studied, we don't see that in the model because we're just looking at this local model for the PDE and we're not considering these global effects. And so because of that, we want to think about, well, how could we model this global blood flow? Now, sometimes global blood flow is modeled through Stokes or something like that, but if we're talking about the whole circulatory system, that's not going to work. Like that would be computationally very expensive. That would just be too complicated. So we want a simpler way to think about it. So what we think about is just thinking about what's going on at certain parts of the body. And so we take space out of it and just think about certain nodes, and then we can develop an ODE. So blood flow can be modeled like circuits, where you have this linear ODE, and this matrix A is impacted for circuits. It's impacted by resistances, inductances, capacitances, and just like the circuit graph itself. So for us, that means that it should be impacted by viscous effects, inertial effects, vessel compliance, and the circulatory system graph. And then also ST is the source term here. And for circuits, that represents voltage. But for us, that represents pressure sources. So if you have added pressure in the system coming from something outside. And then usually the variables of this Y are going to be current and electric potential at different nodes in your electrical circuit. But for us, at these different points in the circulatory system, we're going to be thinking about them as flow rate and fluid pressure. And so here is our whole system together. This is the circuit that we're thinking about. And so our variables of interest that are in that vector Y, as I said, should be pressure differences and flow rates. So across each capacitor, we should have pressure differences. And remember, those capacitors are like different vessel compliance spots. So across each capacitor, we should have pressure differences. And then across each inductor, we want to look at the volumetric flow rate at those points. And also in this connection, because at some point this circulatory system is going to interact with the lamina cribrosa that we model with the poroelastic model. At some point, we're going to have the flow rate and the fluid pressure there. And here we think of this fluid pressure as being, as this capacitor being grounded. And so then this pressure is going to be 0 at the ground. And so our difference is just going to be pi of t. And then the volumetric flow rate is going to be across that inductor. And so then that is going to impact the internal circuit as well. So our ODE, we have, as I said before, but now we're thinking about this QT, which is that volumetric flow rate coming from the poroelastic model. That is like another source into the circuit. And then we have an initial condition on this as well. Okay, so then also remember, we still have the variables here. We have solid displacement, fluid pressure. We also have fluid velocity, which is comes from fluid pressure, but it's going to relate to that Q now. So if we think about it, we really should have that this flow rate across this boundary or this interface for the poroelastic BO model, that should be equal to this flow rate across this resistance. So we should have that V dot N is equal to Q. Also in circuits, we use Ohm's law. There's a similar law for circulatory systems where the flow rate across here, that should be dependent on what the pressure is here and what the pressure is here. And it should really be equal to the pressure differences divided by the resistance. Now, if we put these together, we do get that this V dot N should be P minus pi over R. And then one other thing, though, we have this problem when we say this and this, because Q is just a function of time, but V is a function of space as well. So we have to use some integrals to help us out with that. So one thing that we do is we can average the value of P over that interface and call that capital P, so that Q of T is really just a function of time like we want it to be. And then the other condition where Q is equal to v dot n, we just use that to help us say that v dot n is equal to p minus pi over r. So that comes in with this boundary condition, which is okay because v dot n is spatial. So it's okay that we have something spatial over here. And so this is our coupled model where we have that BO, we have the same boundary conditions that we had before, but now we have this additional interface condition, and then we have the ODE from before. And these systems are really coupled together because this Q of t is coming from this value right here, where this P of t is dependent on little p, and little p is the solution to the PDE. And so to get the solution to the ODE, you really need the solution to the PDE, but to get the solution to the PDE, you need the solution to the ODE because of this pi. So we're really coupled together here. So we want to think about how we could get well-posedness of this system then. And so what we do is we again look for a weak solution to the PDE, where we just assume for a second that we do know what that pi is. And we can do this. I'm going to skip over this a little bit. There's multiple ways to do this. One of them is to use Showalter's theory that he used for the original system, where we introduce some operators, and then we can show existence and uniqueness of the solution. And then after that, we can linearize the ODE, because linear ODEs are much nicer to solve. So we take this y of t and we set it to be z of t. And then we'll get a bound for the ODE. We also have a bound on the PDE solution. And what we want to think about now is, okay, how do we couple these together? Well, we want to look for a fixed point where, say that you're given a y, you take the first component of y, which is pi, and you plug it into the poroelastic model. And then from the poroelastic model, you get that little p, which you can average, you can integrate to get the capital P, and then you can plug that into your ODE right here, and then you'll get a new y. And when we plug the P into the ODE, we're also taking the original y that we started with and plugging that in place of this z, and plugging that into the ODE. But if we can get a fixed point to this map, then we would have the new y here, and the right p there. And so that's our goal, is to look for a fixed point to this process. And so here are our bounds that we have from the ODE and PDE. It'd be really nice if we could show that t was a contraction, but unfortunately we cannot. And so, because we don't just have a constant times the thing, we have these other sources. This comes from the F, S, G, and psi. So we don't have a contraction. But we can show that t to the n is a contraction. And so what we do here is we let m be greater than what seems like a random constant, but this is what we figured out would work, because we really want to say that Tn maps a ball to itself. So if we set m to be this, then we can define this ball, and we can use induction then to show that this is going to be less than this, which is really nice, because then when we get n to be large enough, we can get this constant to be less than 1. And then also we can get this right here, is just going to be, well, this whole thing right here, this is going to be less than half of m. And so we can also get that this is less than m, which is good because we want the ball to map to itself. So when n is sufficiently large, then t to the n, t composed with itself n times, will map this ball to itself, and it'll be a contraction. And so then that means that t to the n would have a fixed point. But it also means that t to the n plus 1 would also have a fixed point, because it would also satisfy that condition of n being sufficiently large. So if we say that Zn is the fixed point to Tn and Zn plus 1 is the fixed point to Tn plus 1, then we have that Tn of Tn plus 1 Zn, that is going to be Tn plus 1 of Tn Zn, because these are just compositions, so I can change how I have those exponents. And then I've said that Zn is a fixed point to Tn, so this is just Tn plus 1 of Zn. But then that tells me that Tn of Tn plus 1 Zn is equal to Tn plus 1 Zn. But Tn has a unique fixed point, so that means that Tn plus 1 Zn is actually equal to Zn, which means that Zn is the unique fixed point to Tn plus 1 as well. So Tn and Tn plus 1 have the same unique fixed point. And so then that means that T of Tn Zn is just going to be T of Zn. And also we can say that Zn is equal to Tn plus 1 Zn, which is that T of Tn Zn. So we have that Zn equals T of Zn. That gives us that T has a unique fixed point. And then what we can do is, if we say that T has, the reason we can say it's unique, because right now we just showed that there is a fixed point. The reason why we can say it's unique is because if there's another one, then we could let our ball be bigger, because remember, these are just fixed points on the ball. But we could let our ball be bigger, and then because Tn has a unique fixed point on this new bigger ball, then the two fixed points would actually have to be the same thing. And so that's how we get our unique fixed point, which gives us this fixed point to this map right here. And so then we have a solution to the coupled system. So future work, when I talked about how to have those two interface conditions, I said that we averaged P to get that capital P, and then V dot n was equal to the capital P minus pi over r. Another way that you could do it is you could say that P actually just has to be a constant on the interface rather than averaging it. And then in that case, you would still need to make your weak solution make sense, you would still then need to average your velocity. So you have to average something, either the velocity or the pressure. And then we were curious numerically, if you make these different choices, well, posedness wise, it seems like both ways work, but numerically, are there differences? And there are. So that is a coming paper looking at these differences between these different choices of interface, because there wasn't really like a good application motivated reason why we picked one over the other. So that is interesting. Also, now to this coupled system, we could explore optimal control problems again. That's some future work. And then we want to show well-posedness of the nonlinear poroelastic model when it's coupled with ODE. Right now we just have the linear one. So there's lots of upcoming projects coming out of this work, and I would just like to thank my collaborators on this work so far, my advisor, Lorena Bochu, and then also some of the later project I've been working with another grad student, Matt Broussard, and Professor Giovanna Guidaboni is our expert on these applications, so just want to give her a shout out as well. And I'd also like to acknowledge that this project was partially funded by the NSF. Thank you so much.
Okay, thank you very much, Sarah, for this very nice talk. So now we open the turn for question, comments. So if anyone has some question or comment, please just open the microphone and ask a question. I have one question. It's about your last comment about some future works. You have an idea to treat how to treat a nonlinear porous elastic?
So for that one, similarly to earlier, I was talking about how you would need a, let's see. I talked about how in this paper they use a multi-valued fixed map, a multi-valued map, and then they used a theorem for fixed points on multi-valued maps. We would need to do that again because even with the PDE coupled with the ODE, if you assume you know the solution to the ODE, you're not going to get a solution, a unique solution to the PDE. And so you're going to have to think about, you're going to have to think about like how you're going to get this fixed point map to work. And I think if you go to multi-valued, you could maybe get it to work because there's similar energy estimates in the nonlinear case. So I think that would work.
Okay, there is another question here in the chat, but I have another one. So Professor Enrique Fernandez Cara, he congrats you for your talk. And he asked about, well, you can read, no? A similar control problem with L infinite norm in the cos functions.
Yeah, so to have L infinity norms, we would need to have like our solutions be in L infinity. And right now our norms are in time and space. And so we would need L infinity in time and space, which is not something that we currently have, which again, for the one-dimensional case, we could get, but at that point we can do the state constraints where it's where you're looking at continuous functions. So we would want to think about how we can get that added regularity.
Okay. Another question. Is there any hope to get a controllability result as lambda goes to 0?
So from an analysis perspective, we can have lambda be set to 0 as long as the control space is bounded and you get existence and uniqueness of an optimal control and the necessary optimality condition. Numerically, that lambda term is really helpful to it. It's a regularizer for the problem. And so you need something there. Another thing that we've explored and have a paper on is when we used bounded variation norm of the control rather than the L2 norm of the control. So there's like different things you can do, but to just take away the control completely from that side numerically will add challenges.
Okay. Okay, my other question was related to controllability as well. So is there any other question or comment? If not, let us thanks again, Sarah, for this very nice talk. So thank you very much, Sarah.
Thank you for having me.
So Anna, please.